We continue with evaluating the determining the behavior of a sequence. Now here I want to point out or remind you that x to the power of n approaches to 0 as n goes to infinity as long as x is a value strictly between -1 and 1. Okay, and of course xn goes to infinity as n goes to infinity if x is strictly greater than 1. Okay, so let's do a few examples. Of course, at the beginning, very simple examples. Let's say an is equal to 3/4 to the power of n, and because here x in my case is less than 1, I'm sorry, this limit will go to 0. Okay, or if you have arctangent of n to the power of n, okay, this approaches to pi/2 to the power of n, right? Because as n goes to infinity, arctangent of n approaches to pi/2, and by this case right here, if x is greater than 1 and pi/2 is greater than 1, then this goes to infinity as n goes to infinity. Okay, so let's do something slightly more complicated. Let's say n squared arctangent of n over 2n squared plus n plus 1, the whole thing to the power of n. Okay, and this is equal to n squared. Now what do I know? I know that the numerator goes to infinity and the denominator goes to infinity, so there is the first obstacle, how much is infinity to power infinity, and then that's raised to infinity, right? So this depends on many factors, right? Depends on, first of all, how this ratio is going to behave. So let's simplify that one. Obviously I can factor n squared in the denominator, so you get 2 plus 1 over n plus 1 over n squared raised to power n, and then you cancel n squared and n squared. Okay, and now send n to infinity, you get arctangent of n over 2 to the power of n, because these will go to 0. Okay, but then as n goes to infinity, arctangent of n is pi/2 over 2 to the power of n, which is pi/4, and now this ratio pi/4 is less than 1, so this will approach to 0 as n goes to infinity. Sorry about that. We're continuing with the same idea. Okay, problem 4, an is equal to 1 over 3 to power n plus 1 over square root of 2 to the power of n. Okay, so the limit of an is equal to the limit of 1 over 3 to power n plus, now if you're not sure what is going to happen with the second one, okay, this is 1 over square root of 2, the whole thing to power n, okay, which is the limit of 1 over 3 to the power of n plus 1 over square root of 2, the whole thing to the power of n, because 1 to power n is 1, right? As n goes to infinity, this is equal simply to 0 plus 0, which is 0, right? Because we said that x to power n goes to 0 as long as x is less than 1. And this is less than 1, and this is less than 1, so we get 0. And the fifth problem, let's say, hopefully this is is making things a little bit more clear. 3 to power n plus 5 to power n to power 1 over n. Okay, here you have to be careful, okay? This is not equal to 3 to power n to power 1 over n plus 5 to power n to power 1 over n. So please be careful about this, okay? Same as a plus b squared is not a squared plus b squared. So the question is, how am I going to answer this? So 3 to power n plus 5 to power n to power 1 over n. One thing is to go through L'Hopital's rule, because the base obviously is going to go to infinity and the exponent is going to go to 0, and this is the undetermined exponent infinity times 0, which we don't know how much it is. And then you take ln on both sides and you do what you know how to do, and that's fine. You can do that. I'm saying that to avoid these multiplications, derivative of ln of 3 to power n plus 5 to power n, and the derivative of, well, is going to be easy. Anyhow, what can we do? Well, I can factor 5 to power n within the base, and then I have 3 to power n over 5 to power n, and then very soon you should be recognized that this is 3 over 5 to power n, whose limit I know. It's going to be 0, right? Plus 1, and that is to the power of n. Now, of course, here I can use this rule, a times b to power n, which is a to power n, b to power n. So this is 5n to power 1 over n times 3 over 5 to power n, this term, right? Plus 1 to the power of 1 over n. Okay, so these cancel, so I get only 5. 3 over 5 to the power n plus 1 to the power of 1 over n. And now, if you send n to infinity, this guy will go to 0 as n goes to infinity, because is a ratio less than 1 to power n. That will go to 0, so you get 0 plus 1, and this one here goes to 0, so you get 1 to the power of 0. It's 1. 5 times 1 is equal to 5. And I will finish this video with something that we talked about in class, and that's the order of growth. Okay, and then we listed these sequences and this symbol here means it approaches to infinity with a quicker rate, right? With faster rate. Maybe this symbol should be a little bit like this rather than, sorry about that. Okay, so for example, if you have n to the power of n, we prove this over n factorial, because n to the power of n goes to infinity much faster than n factorial. This ratio will go to factorial, and logically this will go to 0 as n goes to infinity. Okay, we just have to point out two things here. A should be greater than b, greater than 1. B should be greater than 1, and then this exponent r is any exponent greater than 0, not just greater than 1. Okay, so let's do a few examples very quickly using this order of growth. So example 1, ln of n plus 1 over square root of n. Well, a logarithm of any positive power b, and ln, that means that, sorry, not power, base b, that means the base is e, right? Grows slower than n to any power, and this is ln of m plus 1 to the power of n to power 1/2, any positive power, right? So this goes, as n goes to infinity, this goes to 0, because this is going to be the dominant term, goes to infinity much faster and pulls the ratio towards 0. Okay, ln of n over ln of 2n. Here I'm going to use very simple properties of logarithms learned in high school. Ln of ab is ln of a plus ln of b. Okay, and then either you can just notice that because the dominant terms have a same exponent and same order of growth, and the constant in front of them is 1, you can guess that this limit is going to be 1. If not, just factor the dominant terms. We have ln of 2 over ln of n plus 1. Then you cancel this, and as n goes to infinity, I have a constant divided by something that goes to infinity, 0. So this approaches to 1 over 0 plus 1, which is